And good morning, everyone. From this point on, we are recording for our resource archive. Today's session in our one-year series, we have a grant. Thank you very much to Freshwater Future, who provided the seed money to enable us to do online distance learning, interactive, real-time workshops, training sessions, education programs. Today's session is the third, I believe, in the series, and we titled this, Are We There Yet? Solutions for Water Sustainability in the 21st Century. Let me increase my audio here a little. The reason we chose this symbol as the way to start off all of our presentations is it really shows both ends of the spectrum. On the left is the expectation of what wastewater management meant at the dawn of municipal and central sewer, central wastewater treatment. The job of the wastewater operative was basically to keep the water flowing and to remove foreign objects, in this case, the rat. Last time we used this illustration, there was a pretty droll comment that having an open flame in such an explosive atmosphere was probably not a good idea. But, you know, this was drawn, I believe, in 1895. So on the right is the expectation of what our belief as far as wastewater management, the environmental management, public health management is today, that anytime you come in contact with water, it's your expectation that it's safe, that you're not going to get sick, that you are going to be completely at ease in your bath, in your lake, when you turn on the faucet, that whatever happens is going to be clean and will disappear. And unfortunately, of course, that's why we're all in this business. And at this point, we're going to move on to a quick acknowledgement that many of the illustrations that you see today have been originated from either the Michigan Department of Natural Resources and the Environment, from EPA training manuals, and also from the On-Site Consortium. This is the Decentralized Wastewater Treatment Consortium. You can find them on the web at onsiteconsortium.org. And we also would like to, again, remind you that if you are hearing impaired and you need a written transcript of today's presentation, please send us an email. We'll be happy to provide a written transcript. We're asking that you confine your questions and comments to the chat window at this point, and there will be a question and answer period midway through, halfway through the presentation. And also at the end, we will have a general discussion session. Again, if you have any issues with audio or with tech support, that number was provided to you. Use the chat window to let me know if you're having any audio issues. So at this point, I am going to turn it over to our first speaker this morning, and I'm going to turn my microphone off.
Good morning. This is Dan Thorell with the Grand Traverse County Health Department, and I'm going to be talking about Mound Systems today. And this presentation was really geared kind of towards the basics of Mound Systems. It's titled Everything You've Always Wanted to Know About Pressure Mound Systems, really geared for the homeowner. I see that there's a lot of engineers and some sanitarians in the audience, so I apologize if this is not quite as detailed as you would like, but I would happily answer any questions that I can and go on from there. So let's get started. Well, basically, this slide kind of illustrates that the wastewater treatment is part of the water cycle. It shows what we typically see in our neck of the woods here in Northwest Michigan, the quintessential cottage on the lake with the wastewater system. Here we just have the septic tank, and it kind of illustrates how close everything is, that we're dealing with a lot of fresh water, and we want to do our best job possible to protect that water. And we have certain requirements that we have to abide by to do that. This slide kind of illustrates the traditional septic system where we have the house, the pre-treatment with the septic tank, where we're obviously what we're doing here is we're allowing the wastewater to settle, where we get separation of the things that float and the things that sink. And what we typically try to do in these cases is size the tank appropriately based on the design flow from the house. Usually, in the case of a house, it is determined by the number of bedrooms. And at least in my neck of the woods in Grand Traverse County, we allow 150 gallons per bedroom as our design criteria. So if this is a 3-bedroom house, then we would be designing for a 450 gallons per day. And in our case here, we would have a 1,200 gallon septic tank. What's optimal would be 3 days of retention time. And then as the wastewater flows out into the soil absorption system, or dispersal field, as I like to call it, we have a couple of actions that are going on. We have the water infiltrating, being absorbed into the soil, and going down through the soil and being treated as it goes, hopefully, and eventually it will reach groundwater and vent out to a lake or stream. We also have evapotranspiration, where at least during the summer months, when and we have a nice shallow system, optimally about a foot of cover, we have a fair amount of moisture or water being evaporated through the soil into the atmosphere. Okay, what is a pressure mound system? Basically, it's an elevated wastewater dispersal field that is pressure dosed using a pump. And the pressure distribution and isolation of the dispersal media above the restrictive or sensitive soil conditions, it minimizes the adverse impacts to public health in the environment by elevating that system, by elevating that bed, and by pressure dosing it. We're basically taking the effluent from the septic tank and we're spreading it out over every square inch of that dispersal cell. These type of systems, they don't work on every site. They require proper design, installation, and oversight. In our county anyways, kind of a quick run by about how pressure mound systems are dealt with here. We have permitted and designed mound systems since the early 70s, but for a long time, only until a few years ago, we only did it in the case of an existing home where we had a really bad situation and we had some pretty good soil, but maybe some a restrictive layer at 2.5, 3 feet, or groundwater at that depth. Then we would allow the use of a mound system. Now we have a whole policy and procedure manual that outlines the criteria for doing mound systems for new construction, for existing homes, and all of that. So, and that also, going back, hold on. We also require the installation, the design be designed by a approved consultant, whether that be a professional engineer, sanitarian, or someone else that is qualified in that realm. So this slide kind of just illustrates the number of holding tanks that we have in this county. It's kind of unique. Holding tanks are kind of a unique situation, which we see in northwest Michigan, Grand Traverse County, Benzie County, Leona County. I'm not exactly sure how many holding tanks are in some of the other counties, but at least this has been a practice that's been going on for some time, and where we have sensitive sites that could not meet conventional code, they were allowed to put in holding tanks. So this illustrates kind of the volume of holding tanks and septage, but I really wanted to show for the holding tanks because these are the potential mound systems that we see out there. And when we're talking about a mound system and we're talking about soil treatment of the effluent, we really need to define soil in this case. And it is a porous natural body of mineral, air, water, and organic matter that changes or has changed in response to climate, topography, time, and organisms. So basically it is a living structure that changes all the time, and it can be affected by a number of different factors. But in this case, when we're relying on soil to treat the effluent, we're relying on natural parent soil. We really want something that has a structure, that has a texture that is suitable for the treatment of wastewater and is going to remove nutrients. It's going to have plenty of air to encourage the growth of beneficial microorganisms, aerobic microorganisms that will digest the waste as it passes through the different soil horizons. And what we're looking at for the soil properties, we have what's shown here in this slide is we have a significant, probably a foot topsoil layer, and below that it looks like a sandy loam. At least that's why I picked this slide to kind of look like that, because that, in my eyes, is the most optimal soil to have as far as treatment goes. And there's a lot of question in this arena, and a lot of the codes, including Grand Traverse County's code, is designed. It was basically designed on the premise that the sandier the soil, the better, and that is true for just purely draining water and getting rid of water. But if you're looking at it from a treatment standpoint, that's not really the case. If you just have very clean sand, very coarse sand, our code allows for the smallest drain field, which basically you get point saturation, and you get effluent running through the soil very quickly, and there's virtually no treatment. Well, I shouldn't say no treatment. There is some treatment, but little treatment as compared to a soil like a loamy sand or a sandy loam. A sandy loam soil has fine particles in it. It has some clay content, and it also has some minerals within the soil that will treat the wastewater as it goes through the soil. There's some considerations to keep in mind here. Installation in these type of soil properties is very important. You have to be very concerned with compaction of the soil. You really need that soil structure to be intact, so you have to have an installation that is very conscious of compaction and minimizes compaction, and that's part of the plan. Which is sometimes kind of hard to come by in this neck of the woods, since we're dealing with so much sand. Many excavators are used to just basically installing systems with heavy wheeled equipment on sand, which that's okay, but when you get into situations like this, you have to be much more conscious of compaction. So anyways, getting back on track, we're looking at this topsoil layer, which has a lot of root structures. It's got some air pockets, and it's got that sandy loam classification. And as the effluent from, say, like a mound that was laid above this would travel through this layer, you're going to get excellent treatment. You're going to get excellent growth of aerobic bacteria. The treatment would be in the form of mainly phosphorus removal. The phosphorus ions will get trapped in this layer of soil. And when I'm talking about soil structure, this slide really kind of illustrates that, where we're looking at rapid, moderate, as far as, and then going into slow. And really the ideal soil structure for treatment, not necessarily just getting rid of the water, but for treatment, would be this blocky or prismatic soil structure. And single grain and granular is okay in the heavier soils, but that's be kind of rare in that situation. But that's what you see. The single grain, granular, rapid infiltration is typically what we see in the really clean sands that we have an abundance of in this area. The blocky and prismatic structures are something you see more in a sandy loam, a sandy clay loam. And then on the right, when you see this platy or massive structure, this is typically what you would see with clay loams or clay. These are the typical soil structures that inhibit the infiltration of water. And in these situations, lots of times these soils are not suitable because they just do not allow the water to pass through it at a rapid enough rate to consider them for a dispersal field. Well, we have definitely have some challenges with soil treatment, and as far as the design goes, we always need to look at how soils, poorly drained soils or compacted soil, and that's more or less the clay type soils. In a lot of parts of southeast Michigan, where I used to work for Genesee County Health Department, most of the soil down there was clay loams or sandy clay loams, but really most of it was clay loam and had been farmed for a number of years, so there was a lot of compaction, a lot of poorly drained soil, so there was a lot of challenges with dealing with those soils. And consequently, 95 or more % of the dispersal fields that we installed in that area were mound systems. And that was really the only way that that you could efficiently deal with those type of soils. You spread out the mound, you spread out the system in a large enough area to where you were getting such a small application rate in the parent soil in a square foot area that it was able to take the effluent. Most of the considerations we have around here are high groundwater table and the nitrate and phosphorus loading. Those are the biggest concerns that we have here. Also, steep slopes are some of the bigger issues we have here, and also the like I talked about before, the large rocks and the rapid flow are things that we have to consider because we have such coarse sand areas and rocky areas that we have to deal with. And most of the, like I said, most of the sanitary codes or environmental health regulations say in those cases where you have very coarse sand that you're allowed to put in the smallest of systems, but really in those conditions we should have larger systems to deal with those rapid flow conditions. Some of the soil properties that influence the wastewater treatment is the wetness conditions, where the groundwater table is. If we are looking at some soil that we're going to build a mound over, we need to have some unsaturated conditions to allow the wastewater to flow through that soil and be adequately treated. It is not, if you have saturated soil conditions, you are not going to initiate and sustain the correct aerobic bacterial growth that is needed to adequately treat the wastewater. We talked about water movement through texture and structure. Again, we want a moderate water movement through the soil is the most beneficial for treatment. If you do have a more grainy texture, then we can make the system larger to accommodate that. And really what we're looking at is if we're looking at water movement through the soil itself for treatment, we're looking at it at a square foot application rate and what works best for that particular soil texture or structure. Restrictive zones and horizons. What we're really talking about there is where is that seasonal high water table and where is the restrictive clay layer that we're trying to stay away from. In Grand Traverse County, I can't speak for the other surrounding counties. For a mound system, we need 30 inches of suitable natural soil in place to allow the use of a pressure mound system. And what that means is, some level of topsoil usually, and another down to 30 inches of natural soil in place, preferably a loamy sand or a sandy loam. As I said before, in this area we have a lot of medium sands, a lot of coarse sands, and lots of times we encounter that with a high water table situation in an area where we're going to be using a mound. In that case, then we would be designing the system, laying it out so that we have enough of a basal area in the mound to really spread out that effluent to make sure that it's being applied over a large enough area where it's not going to rapidly move through the soil and impact the groundwater. Give it time to move through the natural soil and be treated. Now also landscape, which Scott Dierks from JF will be talking about later. Landscaping is important around a system also, not only from the standpoint of planting, but also from the standpoint of moving surface water around your particular system. You want to make sure that any surface water created from a road or driveway, a roof, or anything like that can be adequately moved around the area and not away from the particular dispersal field, so that you're not creating a situation where you have a saturated condition next to your dispersal field where you are dispersing the effluent. Now, when we are talking about high groundwater, we want to raise the infiltration area with a mound. And this diagram really illustrates the area here that what I'm talking about. We have the septic tank where we have the separation of the floating layer, the scum layer, and the sludge layer, and then we're drawing effluent from the clear zone into a pump chamber. And keep in mind right here, you see on your screen where I'm highlighting, we would definitely have an effluent filter at this point, and then once we're filtering the effluent to make sure no large particles get through, it goes to the pump chamber, and we want to ensure that that pump is pumping the best effluent quality that we can get out there. Since in the field we're using low pressure small orifices, low pressure distribution lines, which means typically 1.5-inch pipe, and the holes would be 1/8-inch to 1/4-inch holes. But basically, if you look at this diagram of this mound system, as we're looking at the infiltrative surface of the distribution cell here, we have all this sand beneath the distribution cell that the effluent is able to filter through prior to getting to the parent soil. So when we talk about a basal area, we're talking about from this toe to this toe right here. We have a much larger area than what just that distribution box is showing to allow the effluent to travel through. So once it reaches the parent soil, we have the amount of effluent is really, we have a much smaller application rate going on the surface of the natural soils in place than what we would with a conventional system being in the ground. Another consideration here is it shows the topsoil in place, and that is definitely something that we want to see. We want to make sure that the topsoil is left in place because it is a good treatment layer. Typically what we like to see is that the topsoil is mowed down, flushed with the ground, and then roughened up with some backhoe teeth on a tracked vehicle during dry weather conditions, because that is also an area that could be of concern if you compact that topsoil layer. We want to make sure it's not compacted, that all the pore spaces and interstitial spaces between the microscopic grains of soil are intact to allow that effluent to enter that area and get the best treatment as possible before it hits the groundwater layer. Now this diagram kind of shows where our wastewater is coming from, and this illustrates what we're going to see going into the system. Just thought it was a good representation because people typically just think about the toilet, and that is really 1/4 of everything that goes in. If we look at laundry is the second highest, and then showering. But one component here, because we also want to talk about in a mound system not hydraulically overloading the system, is which is surprising, is 13.7% for leaks, which that's always a concern when you're designing a system. I think is really, if it's for an existing place, is talking to the homeowner and making sure that they're aware of where all their wastewater is going. Making sure that their plumbing is in adequate functioning condition, and that we don't have this extra water going into the system. And then also a consideration when constructing a new home is just basically using low flow fixtures. Making sure one of the other things is that in a lot of new homes these days they install humidifying systems on the HVAC unit for the winter time to take care of the humidity, and that can also introduce a lot of water, just clean water, into the system, which really doesn't need to be there. We always recommend that those type of things be routed to a separate system, as well as a water softener. Supernate, which is the discharge from a water softener, the brine discharge, if you will. We always recommend that be routed to a separate drainage system. 99% of the time it doesn't happen. Plumbers are just used to basically routing water softeners into the sanitary. But those are considerations to think about. This slide illustrates the soil treatment of septic tank effluent at varying soil depths. And the interesting thing here, this is tank effluent. This is not influent. This is effluent. If this is what's coming out of the tank, so it's been treated using anaerobic treatment processes in the tank. And then after 24 inches of soil infiltration or filtration, the BOD reduces significantly. The nitrate level goes down, or actually goes up, I'm sorry, because of the nitrifying bacteria in the soil. There would have to be a denitrification process to reduce that, which doesn't happen unless you're using a treatment type system. But anyways, as you can see, this is total phosphorus. TP means total phosphorus. And that from the tank effluent after 24 inches of soil goes down significantly. What's interesting here, also should be mentioned that the bacterial log detection is no detect after 24. But the thing that's interesting here is after 48 inches, things are not that much different, except when you get with BO2, except when you get to nitrate and phosphorus. The nitrate can either go either way, up or down, and that really probably depends on what's going on in that particular soil environment. Phosphorus just gets removed to a further extent because it comes in contact with more soil, which has more removal capability of trapping that phosphorus ion. Well, when we're talking about these systems, we're talking about low pressure distribution, and the reason that we like to see low pressure distribution is because we get uniform distribution. We're not in a typical gravity situation or a gravity. There are gravity mounds out there where you would just prop the house up really high, maybe put the then keep the tank up high, and then just build basically a shoebox in front of or behind the house. In those type of situations, what goes in, what goes out. So if 50 gallons go in, 50 gallons go out, and you're relying on how well the pipe was installed, how level it is, how well it was backfilled to get uniform distribution, and it's very difficult and doesn't really happen. With a low pressure system, you are ensuring uniform distribution, meaning that every single square foot of that field is being dosed. You can set it up so your pump chamber pumps a small volume. It can be spread over a large area. You're maximizing the soil contact time. You can play with your dose, so you have a small dose, large rest period, or I mean large dose, long rest period, or you can do smaller doses, micro doses, if you will, in shorter rest periods. There is some debate whether which one is best. What I like to do is do for say like a typical 3-bedroom house, no more than a 100-gallon dose. Then I think that the field gets dosed typically twice or 3 times a day during normal operation, and you get some rest period overnight. You get some aeration, which follows the dose of the effluent. You don't have this gravity effect where you're just getting a point saturation into a gravity field near the header end of the field until such time that it forms a biomat. You're getting aeration, you're getting the air in there. It's really the most efficient way to spread out the waste and to get the most efficient treatment possible. Some other advantages would be to, we talked about the uniform distribution. The other advantage would be to provide a measure of the flow by using an event counter. And what that is it's a counter that counts every time that the pump turns on. And if you know that you have a pump that is pumping 30 gallons a minute and it runs for 3 minutes, and you know that you have every time that pump kicks on, it's dosing 90 gallons. So if you keep track of that event counter, you'll get a very good measurement of your actual flow coming from your home or commercial facility. And really, there's very few residential homes where you see event counters. Most of the time you see them in commercial type applications. This is just another diagram of kind of illustrating pressure distribution, where you are spreading the effluent uniformly over the absorption area. With a mound, you're going to be spreading it across the length of the mound. You're going to be maximizing the effluent contact with sand or whatever other type of soil that you have. With small doses, I think is optimal, and you're going to get the best treatment that you can get over time. Some of the components of a pressure distribution system, basically, you have after it leaves the septic tank, you have your pump chamber, the pump controls, and a force main, which is typically depending on the length that you're going to be pumping, would typically be a 2-inch force main, a 2-inch pipe, and that is going to go to your dispersal field, where you will have a manifold or a header, however you want to say it, and you would have laterals with orifices, and the laterals are typically 1.5-inch diameter laterals. The orifices, like I said before, are typically 1/8 inch to 1/4 inch. It should be noted that using the smaller diameter orifices is more beneficial as far as getting more orifices throughout the dispersal field with using a smaller pump, and it is almost logarithmic as far as the number of orifices you can gain by going from 1/4 inch to 1/8 inch with the same pump. So basically, using 1/8 inch orifices, which are the smallest, a lot of people have concerns with hole plugging and whatnot. You just have to make sure that you have adequate filtration and you have a larger residual head at the end of that you're pumping at the end of the lateral to ensure that you have enough scouring velocity to get through those orifices and to withstand any possible plugging. And with that, you also want to provide some provisions for lateral flushing, which would mean using some cleanouts or sweeps at the end of the laterals. A 90-degree sweep where you have a valve and you can actually access the interior of the line and flush them out using a jet type hose or a bottle brush type application. And one of the other things, if you're using a pressure distribution system, whether it's a conventional system or a mound, you want to be conscious of some monitoring, some management, and some maintenance, because you have a lot of moving parts in there. You have a pump and you have some sort of float mechanism, unless you're on a timer. And these are all things that you want to be conscious of as far as on a maintenance schedule and checking to make sure that they're all operating properly, as well as the effluent filters that you may have in place. You want to make sure that those are checked and cleaned as needed to allow the system to continue operating. This slide really demonstrates what a possible pressure mound or a pressure system, low pressure system design may look like. This one in particular has a center manifold. Sometimes they may be on the end. You may have the manifold on this end and just have long laterals, and that's really in normal applications you see that more often. Center manifolds, we like to see or like to design those when we have a really long, say a long mound system, which is really the type of mound system we like to see. We like to see long, narrow mound systems, maybe with a distribution cell of maybe 8 feet wide, 125 feet long, and you get a very long, narrow mound. What that does is it allows free flow of air throughout the mound. The longer and narrower, the better. Of course, a lot of sites don't allow that, so that would only be in the ideal situation. So getting back to this slide, looking at the layout of the distribution laterals, these would be your 1.5-inch laterals. This would be your 2-inch, or it could be 1.5-inch manifold. This is your 2-inch force main coming from the pump chamber, and sometimes this could also be 3-inch depending on the distance. If you have a very great distance to cover, if you go from 2-inch to 3-inch diameter force main, you're gonna gain back some head loss that you would have in that 2-inch line. What this is shown here, this shows the, if you can see where I'm marking here, shows the sweep 90s that allow access to the laterals for flushing, and this kind of shows what can happen inside these laterals, the buildup that could occur if you are not flushing those periodically and cleaning those things out. So I think that illustrates that pretty well. This basically is just another picture of, again, a center manifold type system here. This being the manifold, and this looks like it is a 3-inch manifold going to 1.5-inch lines, or maybe even smaller. But this also shows the sweep 90s on the ends for access to the lines, and you really can't see them very well, but these are the orifice shields that go over the small diameter orifice. And what happens is the effluent sprays out of the orifice and hits the back side of the orifice shield and kind of trickles into the stone from there. On this particular system, they are pointed down, which it can be either way. I think a lot of people don't use orifice shields if you're pointing the holes down, but I think it's a good idea because there's a great potential if you're especially in a stone system, where you could have a stone or a rock plugging that small hole that you may have. This over here shows an orifice, a round orifice that is on a hole that's pointed up. So it just kind of shows you the different orifices or orifice shields that you could have. And right here, this gentleman is putting on a valve cover, which is kind of typical you would see in irrigation. To protect that sweep 90 and to protect the ball valve there, and to limit access to it as well. So, and here is our orifice shield. This is just one kind. There's also ones that are round that would clip on the pipe as well. This one just snaps on the pipe, and the orifice might be right here, and it might be just like I said, anywhere from 1/8 of an inch to 1/4 of an inch in size. When we're talking about management and maintenance of our mound system, our pressure distribution system, we want to inspect the observation tubes for ponding, and I guess I really didn't talk about observation tubes, but basically if you have a what we typically see as a 4-inch piece of pipe with holes drilled into it that is placed inside the stone of the distribution cell. And what you want to, and it would have a cap on it, and it would come up above the final finished grade of the mound. And what you'd want to do is pop the cap off and look in to the system. And really, what you're doing is you're looking inside the stone where a water level may be inside the stone. And ideally, you don't want to see any water ponding inside that observation tube. But anyways, it's good for monitoring the condition of the stone as far as the level of water that may or may not be in there. You want to inspect the system for any infiltration of water from a source that you don't want to be in there. And that would just basically be consist of popping the lid on the inlet side of the septic tank, and making sure that all the plumbing fixtures in the home are off, and looking for some flow coming into the system. And like I said before, you may have an HVAC system that has a humidifier which runs a constant stream of water over a filter, and whatever is not taken up by the air system, which is most of it, flows into a drain and into presumably a septic tank, or preferably a clean water dry well. So that's some of the things you would be looking for. Other things may be a leak in the plumbing, a leaky faucet, a leaky toilet. So that would be definitely high on the list of things to look for when you're doing an inspection of a system. You also want to look at the sludge and scum layers in the septic tank and determine the depth of each. At a certain point, the tank would need to be pumped, and typically, what I always tell people is you want at least about a foot of effluent below the outlet baffle before you hit that sludge layer. So if that sludge is coming up and it's you're getting pretty close to that outlet T or baffle, then it's time to pump. Same thing with the sludge layer. If you're getting up to a foot of scum layer, if you're getting up to 6 inches to a foot of scum, then it's probably getting time to where you need to pump that tank. And also the flushing of the laterals. That's something that needs to be done periodically to keep the system, keep your distribution laterals free of getting plugged up from within. One thing that you can do to check, typically when we design a system, let's say it's with 8-inch orifices, we would set the residual head, meaning the head pressure at that sweep elbow. We would set that at about 5 feet. Well, if you wanted to check that again after some time, ideally that residual head would still be 5 feet. If you check it and it's 6, 7, 8 feet, then that's a good indication that you are getting some hole plugging in the laterals. Because less effluent is going out through the orifices, you have more pressure built up inside the actual laterals. And that's, I guess, is the next point here that I already went into. And of course, if you were in that situation, after you check the residual head pressure, you would clean out send a bottle brush down there if needed, or a jet hose to clean out those laterals. This diagram shows your typical control panel, and really I just wanted to show this as kind of a general picture of what one might look like. Of course, you may have, there's several different manufacturers out there, there's several different kinds, but basically you have a relay, you have the contactors for the pumps, and this is where the pump and the floats would be wired into. You have a terminal slip where they would be, where the pump would be wired into, and the alarm, and every component of the control panel. And some of them actually have a circuit breaker inside, which is beneficial if you're doing some maintenance on the mound. You can actually hit these circuit breakers to turn off the power before you pull a pump pull some floats or whatever you're doing there. A nice or a big component of the system would be the actual alarm, and you will have, here's the audio buzzer. For a homeowner, you would have, when you're looking at this, if you hear this thing going off and you see the light on this thing going, you have a problem, and you need to, basically the first thing you need to do is stop running water into the system, and then you want to call your maintenance provider, or if you're a handy homeowner, you may want to pop open the pump chamber and check things out, see what's going on. A lot of some of the other things that you may see in a control panel would be a run light indicator, meaning that this light is turning on when the pump is running. And there are some control panels out there that actually have LED lights that show when a float is on the on position, which can be helpful if you're trying to diagnose any problems or making sure that the system is running properly. Now if we get into the different type of floats, there's really two different type of floats that we're looking at, and we have a mechanical or mercury float type system, which is this guy right here. And what happens is when this float floats up this way, when it gets to about this point, it will turn on. There's either a ball bearing inside that will move and activate will contact the contactor and activate the system, or more commonly mercury. In recent years, because of the hazards of mercury, a lot of manufacturers have been getting away from mercury and going with mechanical. Not quite as good as mercury, if you can imagine. I mean, mercury, being liquid metal, can flow pretty freely. A mechanical type float, you can always have some problem in there where the ball bearing is not gonna contact. And I see from Larry Stevens has a comment, from a maintenance standpoint, both an event counter and an ETM should be included, and I would agree. We don't have it in our code that we have an event counter, and for any future revisions we probably should include that. In residential settings, you don't often see it, but I agree it should be part of the system, because it is invaluable when you are trying to troubleshoot a system and determine what went wrong when something went wrong, especially with the dispersal field, as far as any premature failures go. Next is a vertical float switch, and this is also a demand dose, and this simply is what it says, is that when the effluent rises, this little guy right here just moves up this rod and turns the pump on. Pretty self-explanatory. This slide just kind of illustrates the different alarms. You can have indoor alarms where this is actually mounted inside the house, and you have a light and a buzzer here, and this would indicate, obviously, to the homeowner that you have a problem going on, and you have an alarm going off. Usually in these type of situations, it's a pump problem. And let's see, we see this a lot. We see alarms mounted outdoors on a pedestal, and this, like I was showing you with the control panel, could be just part of the control panel. Sometimes you just have an alarm set up out there. It depends on how complex the system is. Sometimes they're just simple, pretty simple, to the point where they just have an alarm setting outside in a junction box. So. Again, this is really just showing the typical Mound system components with the septic tank, the effluent filter, the dosing tank, and the mound itself with the distribution cell. And I wanted to talk a little bit about minimum horizontal isolation distances. And what we did in Grand Traverse County is we pretty much adopted the DEQ, now the DNRE, their guidance mound document. We adopted their isolation distances, And some of the ones that we have a challenge with, especially if you're looking at a lakefront lot or a riverfront lot, is getting the 100 feet from surface water in order to use a mound. But we also have provisions for doing an advanced treatment system where if you're inside the 100 feet, then we can pre-treat the waste to allow that application to be used in that case. Typically, we have 50 feet from an individual well. From basement foundations, we have a 50-foot isolation from basement foundations. And this should be noted that we really only adhere to that in a situation where we have new construction, and it has an asterisk that says the downslope edge of the greenbelt area may be located within 25 feet. And really what that means is if you have a sloping site and the house is down gradient from where the system is, there's a green belt associated with the mound, and furthermore, the basement would need to be 25 feet from that. And like I said, if we have an existing home, existing situation, we don't really follow this. We go back to our standard environmental health regulations, which could be only as little as 10 feet from the home. When we're talking about a drop-off, we mean like the crest of a hill where it just shoots right off and there's no slope at all down to grade to speak of. A very steep drop-off. We want to stay about 20 feet from that, just so we minimize any possibility of erosion of that bank impacting the system or any bleed out possibly from the system going over the top of a hill. Typically, 10 feet from property lines. That's not much different. And then we're talking about footing drains installed in water table without direct connection to surface water. We want to be 25 feet. And then footing drains installed in water table with direct connection to surface water 50 feet, which makes sense, I think. And this we don't see very often. Drains designed to lower water table, I think that's more of a downstate concern there. But we don't see anything like that around here too much. This diagram kind of shows us a site plan, and this is what I mean by the greenbelt area, and this, being slope going. Whoops, losing my arrow here. Slope going this way. I guess it shows it over here. And we only require this downslope greenbelt area where you don't have any other homes, anything constructed in that area. Even sheds or garages or whatnot, which could be impacted from the effluent from the actual mound system. You want this green belt area to exist because the effluent is going to be moving in this direction, coming out of the basal area of the mound, and you want it to have an undisturbed area where good treatment can take place. And if we're talking about slopes, it should be, this is a good slide that would indicate the different names for different parts of the slopes. We have the summit, which is at the top, and the shoulder, just very close to the top. And then the side or back slope, which is the area that we would want to see a mound system if we're going to put one. It would be a long, narrow system following the contour of the slope. And this is the area that you'd want to see that. You don't want to put one necessarily up here, and you don't want to put one down here because you are going to have more saturated soil conditions in that foot slope area and also at the shoulder slope area. Where you have rapid surface water movement across this area is going to have the most unsaturated conditions in the best location for a dispersal field. And also, because we have a drainage way here, which may or may not be containing water, the most isolation from that. Just running over some pictures of different mound systems. I've been talking about your traditional stone and pipe type mound system, but this is a picture of a mound. Actually, it's one that I own, and I constructed it myself. Of using low pressure lines in chamber systems, and the low pressure line is suspended inside the chamber using zip ties, and the 1/8" hole, which is what we used, spaced I think about 2.5 to 3 feet apart. The orifices were spaced. They're pointed upwards, and they spray on top of the actual chamber. And this, I decided to go with this design for a couple of reasons: ease of installation, and I just thought it was a really innovative and good design for a mound system using low pressure. Gravity, I'm not so sure, because these chamber type systems are open on the bottom. In a gravity situation where you have you're putting it into a mound, so you have a sensitive site, you're going to point load this front end right here in a gravity type situation, and you're going to have saturated point saturation, saturated flow in this area until a biomat forms, and really that's going to take a long time, and it's going to slowly creep towards this end. So on a sensitive site, I would not recommend using a gravity type mound system. Low pressure mounds work great. Also illustrating the use of a tracked equipment. Obviously most bulldozers are tracked. However, if you don't want to use like a heavy tired equipment like a loader or a heavy backhoe on a site like this, as long as they stay off to the side, it's possible they could use that. But more appropriately, using tracked equipment like a tracked excavator would be optimal during dry weather conditions. This is just showing a couple of situations where they're not quite optimal. This, I don't know if you can see this or not, but there is the mound system, and here is the stormwater retention. Probably not the best design. I don't know which one was here first, but in this situation, I always say that the wastewater system takes precedence. It trumps everything else. So I would say you would want to reroute this area farther away, at least 50 feet. Again, because you have all this surface water ponding here, creating saturated soil conditions here. How far does this go this way and impact the soil conditions beneath the mound? Functionally, there's probably not going to be much of a functional standpoint here that's going to be affected, but from a treatment standpoint, you definitely could be affecting how well this mound is treating the effluent before it enters the ground here and hits the groundwater. In this situation here, for this one, we have a very large mound with a very steep side slope with lots of trees hanging out right next to it. I like to see for this particular scenario, I would like to see a more gentle slope, getting the toe of the mound down, and then also getting trees a little bit, if they're this close, they probably need to come down when you're constructing that thing. A lot of people, really are into their trees, and I love trees too. But in this case, something's got to give, and I think for the overall functional longevity of the system, having trees that close is probably not the best idea. This picture also illustrates a mound system that was constructed here in Grand Traverse County. It is pretty self-explanatory as far as we have about 18 inches of fill where this 1 foot layer of stone and pipe was installed on top of that, and then when it's all said and done, we'll have about a 3.5 foot mound. This shows an observation tube down on this end, and I think there's another one here, but we can't see. And this shows the 3 laterals with 3 sweep 90s, which indicate the access to the laterals for maintenance, for flushing and cleaning and checking the head pressure and whatnot. This is another picture of that same particular mound. And even though these trees right here, they look like they are closer than they are, they're a good 20 feet from the base of this mound here, which I would say is adequate, depending on the type of tree. If these were all willows, I would say maybe 100 feet would be good, but no, I'm just kidding. But anyways, going on, just another picture of the same particular mound. And as you can see, this is where the topsoil on the ground was roughed up. It was mowed down, and the particular excavator had a doesn't show it here, but he had a mini excavator which has a very light pounds per square inch compaction rate, and he got on this and prepared the soil on top on the ground surface there prior to applying the sand fill, and used the teeth of his bucket to basically scrape up the surface and prepare the soil for placing the sand. Well, that pretty much concludes my talk today. Again, my name is Dan Thorell, and this is my contact information. If you'd like to email me, if you have any questions, you know, down the road after we're done with this thing that you'd like to clarify, or you would like me to send you our pressure mound system policy and procedure manual, which is basically a design manual that we use in Grand Traverse County, I would be happy to do that. And I think we have some question and comments here, but our next speaker will discuss how to avoid unfortunate surprises. As you can see from this, there are some hazards out there, and you really want to be conscious of where things are located and what you're doing there. Although it looks like a concrete take, I don't know that you could necessarily know that this is going to happen, but you might want to wear a life vest, I guess,
we are running
in this situation.
Here,
but
so
I can't even imagine having something like this happen. But doesn't look like a whole lot of fun.
Scott gets the time
so with that, I will
needs.
hand you back over to Dendra.
So we can do a sound check.
All right.
Okay, I'm going to log out, and we are.
Great. All right. Thanks, Dan and Dendra. I have called this. Well, first let me just say it's a pleasure to be here and have the opportunity to talk about what I'm calling somewhat facetiously wastewater scaping, turning a drain field to an amenity. One more housekeeping item. We have here one little issue. We have a rooftop fan that may come on during my presentation. It may cause a little feedback. We've been trying to get it to turn off. Right now it's off, but I can't guarantee it will stay off. So bear with me. Hopefully you'll be able to hear me all the way through. All right. I want to talk. Basically, I want to leave two items, two take-home items for everybody to take home from at least my part of the session. One is this notion of dominion over the earth is, I guess I would say, I think, unsustainable. And you can see the quote there from Wes Jackson, an advocate of sustainable agriculture, that nature must be the standard. So the first take-home message I want to start talking about now and hopefully hit on in the end is that it is of stewardship, that we have to approach our impact on the earth in terms of as stewards. The second point I want to make is that everything that goes around comes around. Somebody's wastewater is somebody else's food. The saying at the bottom there, muck is the mother of the meal bag. When they're talking about muck there, they don't just mean dirt. They're also, this is a saying I think from the 1700s or 1800s. We're talking about human waste, fertilizer, if you will. Again, going back to the notion, what comes around goes around. All right. So those are the two take-home points. Hopefully I can emphasize those as we go along. Outline for my talk, from eyesore to amenity, and what I'm talking about is both a shift in how we do things as well as a perspective on how we view things. Why go native in terms of plants and not in cultures? Potential benefits to your yard with some of these ideas or guidelines from wastewater scaping, and then last part of the presentation I'll try to present some of these couple of slides on guidelines. So let's start with air skin. Basically, Dan touched on this in a couple different places. I am a civil engineer by training and a hydrologist, and have been at JF now for about 5 years, and have become fascinated with plants and their impact on our environment. And as I've become fascinated with plants, I've migrated to a better understanding of dirt, what we might call dirt. It's actually soil in the rooting zone where basically plant roots exist is known as the rhizosphere. That area, that rhizosphere, is where, Dan pointed out, we basically have our topsoil. That topsoil is developed both from abiotic processes, physical and chemical weathering, basically, at least in some parts of the country, weathering of bedrock. In our part of the country, not only do we have weathering processes, but we, of course, have the Ice Age and glaciers moving soil back and forth. In some cases, for instance, up your way, I'm down here in Ann Arbor, a lot of sand. But the key here that I'm going to start to talk about is the biotic portion of the soil, the life portion of the soil. I've read a statistic that in terms of diversity of life, there's actually more diversity in that rhizosphere across the planet than there is above the rhizosphere. Granted, most of that diversity is in single-celled bacteria organisms, but there is a tremendous amount of life in the Earth's skin, if you will. Common organisms that you can find in the rhizosphere, bacteria and fungi, are probably the most diverse, prominent, and abundant species in the rhizosphere. Nematodes, arthropods, protozoa, earthworms. Some call earthworms the planet's ecological engineer, basically converting organic material, creating burrows, and also creating surfaces for other plants to live, other organisms to live. With life, so to speak, in the soil comes structure. The bacteria, the fungi, the plants, the plant roots have what are known as exudates. Basically, they secrete enzymes and proteins that help bind inorganic soil together, the abiotic part of the soil, the mineral part of the soil, into microaggregates. These microaggregates are also bound together by root hairs and fungi, hyphae. And then within the soil medium, spaces are made by burrowing animals, roots and dying roots, literally creating pore spaces within the soil and structuring the soil as well. With structure comes life. So those two titles obviously are circular, the point being that these are self-reinforcing processes. So as plants in the biota, the rhizosphere biota, start to, if you have a healthy soil and you have vigorous life in the rhizosphere, they're actually changing, the life in the rhizosphere is changing the structure of the soils. The physical structure via roots actually promoting gas and water exchange. The soil organisms themselves help cycle nutrients, and soil fertility or soil health is largely dependent on nutrient cycling. Other benefits that accrue from a healthy soil, a soil filled with life, of course, is better resistance to diseases and pests. It's a more robust system. So the benefits, so to speak, for us, and I like to talk about this in terms of exploiting the healthy soil. I think sometimes it puts it into perspective. Again, I say that somewhat facetiously, the idea being here to start to think of ourselves more as stewards than having dominion over the planet. So these benefits that accrue from having a healthy soil, better water storage, better water infiltration. Healthy soil with vigorous root growth is going to help soil stay in place. You actually have, not only will the soil take care of the kinds of pollutants that come through domestic sewage, but you can actually degrade hydrocarbons. Even there are other things, even other chemicals like PCBs, even though it's a slow breakdown that can be broken down in soil. Pesticides, the same spot, so to speak, where you can absorb phosphate ions, or I should say, the same medium that binds phosphate ions can also bind heavy metals. Healthy soil will also convert fertilizers to soluble forms available to plants, like phosphorus. Healthy soil, again, promotes rapid and vigorous root growth. And just to remind ourselves that this rhizosphere, the skin of the earth, is basically the growing medium for much of the planet's primary producers, basically where we get a large part of our food. All right, now I want to move over to the discussion a little bit about natives. This graph right here this image represents a comparison of native plant root growth to Kentucky bluegrass. If you look at number 10 on the right-hand side of that figure, and then you look at the axes, the vertical axis is in terms of feet, so you can see in the blue 0.2468 feet tall, and in the green 0.2468, 10 feet below the surface. Kentucky bluegrass is neither from Kentucky nor is it from the United States. It's an imported species, and you can see the way we maintain Kentucky bluegrass, a couple inches of growth in the top and a couple inches of root growth beneath the surface. Now you look at the natives, and you can see that you're basically looking at plants that have co-evolved in our harsh or rapidly changing Michigan climate, having to deal with droughts that last months on a time, having to deal with rainfall, cold temperatures, etc. These are plants that are hardy and don't necessarily need a lot of attention because they've adapted to the conditions that are here. What does that mean? Go back to this notion that plants are literally changing their environment. This figure is taken from some work on Iowa State. They went out on a riparian area. It was riparian cropland. They replanted the cropland in various riparian buffer species, switchgrass, mixed grass filter, and silver maples. So they planted the same area that had been farmed, and I think it was mostly corn. They went out 5 years later, ran infiltration tests, basically in the pasture, in the corn area. I guess they were also planting soybeans. And then in the areas that have been replanted in the grass filter, switchgrass, and silver maples, and you're looking at an increase in infiltration rate, the percolation rate, on order of something like 5 to 8 times increase within 5 years. Basically, again, the notion here that the plants are not passive. I came to this thinking they were something in the background, but they're literally changing their own environment. One other thing I just wanted to, again, talking about plants as active. This is another graph here representing relative evapotranspiration rates. You see soil is the open square. That's evapotranspiration rate for this particular period, basically a summer period in the eastern United States. Water is the closed diamond, and then you basically have Salix babylonica, which is willow, Acer rubin, red maple, and then Typholatifolia, which is basically cattail. And I just want to point out that if you just look at the willow, going back to water use by plants, and you look at the willow in the closed triangle, you're looking at evapotranspiration rates that are 4 to 5 times higher than evaporation from a straight open water body. So significant water use. These are the attributes of plants are things that we need to understand, both from the respect of what we can exploit, as well as maybe in some cases what we need to avoid. The notion I'll talk about a little bit later here, though, is that, as Dan alluded to, probably not a great idea to plant a willow next to a drain field where that willow is going to just go around essentially hunting for water, and with that drain field there, it's going to find a nice convenient spot to grow into. Okay, so Dan did a great job kind of detailing mound systems. I'm not going to talk about the mound system design per se in terms of moving water within the mound. What I want to talk about is what we do in order to, I guess, wastewater scape around the mound. So the mound functions, again, Dan went through this, so I'm not going to cover that in too much detail, but jump right into rules for wastewater scaping. So I had summarized these rules. Let me jump ahead one slide, a couple of slides. I just want to note at the bottom of this slide you're going to find a web page it's a handout that describes some of these, I guess, wastewater scaping rules in a little bit more detail. I'll come back to this slide in a second. Anyway, I've summarized some of these rules, some from Wisconsin, some, I guess, that we've developed as a firm moving forward. First point is know your options. And again, this is just a summary. What I mean by that I'm referring to is in terms of, for instance, if you were looking at a lot and it was brand new construction, I mean being thoughtful about where you're going to place everything, looking at the lot as a whole, and then paying attention to where your mound would go and how you could landscape or wastewater scape, if you will, in and around your mound, either to hide it, to de-emphasize it, and potentially to take advantage of some of the benefits, particularly of native plants. Get involved as early as possible. Again, this is really targeted at homeowners. I'm saying here from the perspective of design, from the perspective of location, from the perspective of understanding your entire landscape for your entire lot, and then working within that context. Of course, respecting setbacks and gravity. Again, Dan covered a lot of that. One of the things that might be helpful is to, when you're trying to figure out how you're going to do layout, looking and dividing up, here I'll jump ahead one slide, dividing up your areas in terms of landscape type. For instance, in these images right here, you can see alternative locations for mounds or drain fields, A, B, C, D, and then various ways of essentially incorporating that mound into your landscape, or if you will, either hiding it or de-emphasizing the mound in the middle of your yard. So you can see basically this kind of continuous, graceful concept line for layout, dividing the types of landscapes. You can see smooth, continuous, curving line, no straight lines. It's more pleasing to the eye. And again, just mentioning here, trying to move away the focal point, away from the mound, another thing to keep in mind. Continuing on with these wastewater scaping rules, excuse me. Another option is extending or melding basically your rise in the earth where you've got your mound, turning it into a berm, bringing that berm back into other existing landscapes. You can use retaining walls, but only on the upstream side, so you could work up against a driveway, that kind of a thing. As I mentioned before, always design the entire space in mind. And whenever possible, use natives. Again, here's another layout. You can see here what we're looking at essentially on most of the septic is lawn. The large tree on kind of the south side there. Getting back to Dan's point, you're going to see a couple of recommendations at the end of this slideshow. One of them being our recommendation is not to plant, or I should say to plant trees so that the setback from the septic system is at least the radius of the full crown of the tree. So for instance, in this image right here, they've actually, there's a little encroachment upon that rule. If it were us, we would move the tree back so this edge was against or towards the bottom of the mound system, so the tree would actually be located down here. Again, the notion being trees, particularly some species with deep roots, are going to go looking for water. If you've got a system where you have small perforations, an eighth of an inch, a quarter of an inch, there's always a chance if you set this stuff too close to your system, you're going to start to fill in those holes, and it's going to be a real nightmare. You're not going to be able to spray them to simply get rid of the roots. It's not going to work. So now we're talking about, and you'll see again as we talk about rules, really predominantly grass on the top of your mound system, your discharge system, basically looking for, in this case, I think fescues is what we recommend. You can get a great set of healthy fescues that will survive both in the shade and in sun. There are drought-tolerant fescues, and our recommendation is to let them go, not to mow on top of the septic system, not to drive on top, or I should say the discharge system, the mound system, and then basically having these accent areas or these areas that you're going to hide the mound. And then we would say too that you could probably get some of these flowering natives and start to accent too, and actually come up. You can come up, I would say, on the edges and the sides and the corners with your natives, but not covering your entire mound with deep-rooted prairie native species, because again, you may run into issues with those roots looking for water. So here's an example of basically a mound distribution system, left, so to speak, or planted with natives. I think we have a little blue stem, and I can't tell you, I haven't had a chance, I did not figure out what the white stuff is, not my project, but I just wanted to show this example of a mound system. It's I don't think it's bad at all. Okay, one quick little commercial. I just want to also talk about, I just want to mention treatment wetlands. And this is a notion, Dan had talked about if you had sites where you were particularly constrained, you might have to do additional treatment. These are systems that we design where you're literally creating the water surface is just below the surface of the system, so you never see ponded water. The water comes in on this side, flows through the planted medium, and then discharges on that side. And these systems can look like this and this. And in fact, going back to the notion of being stewards, improving soil quality, we would actually advocate the use of natives everywhere. These are roadside swales. This is actually a rain garden, taking the rooftop runoff from a small school. And this individual is my daughter. So she gets dragged out on these adventures sometimes. This is within a parking lot up top. Again, this is basically taking stormwater, treating stormwater. This is the one to the bottom, taking rooftop water, all planted with natives. One more example. This is 150. This is the same area. This is a 150-foot long, 50-foot wide street stub in the city of Ann Arbor. We basically took the pavement off and turned it into another rain garden, and it's essentially now become a mini park. Do these things work? Do planted landscapes actually provide water quality improvements? The evidence has been mounting for years and years. Clearly, on the left-hand side, we're looking at some average treatment wetland results. We're looking at total phosphorus removal in the 70 to 80% range, total metals virtually completely removed, total Kaldol nitrogen one of the forms of organic form of nitrogen you're going to find, you're looking at about a 70 to 80% reduction, and then total suspended solids, organic chemicals, bacteria, all reduced by, and again, this is on average 90%. These native planted swales, again, you're looking at fairly significant phosphorus reduction, metals reduction, nitrogen reduction, total suspended solids. Other things I want to mention about native plants, drought and disease resistant. Again, these are plants that have grown up over the thousands of years within the Michigan climate and Michigan pests. They have evolved to form to take advantage of their own little ecological niche, and tend to be very robust systems. One of the other beautiful things about native plants is once you get them established, and a lot of times it will take a couple of years to get them established so that they're growing vigorously and you keep out invasive plants. But once they are in and doing well, you don't need to water them, you don't need to fertilize them, and you don't need pesticides. Many natives are long-lived perennials. Another advantage to flowering natives, of course, they're going to attract butterflies, hummingbirds, bees, both domesticated bees and native bees, and other beneficial insects. Perennials, the natives are often hardier than their cultivated cousins or imports. The native plants, one of the nice things about native plants in terms of, again, their effect on the rhizosphere, something in the order of 25 or 30% of the native plant roots die every year, and you're going to get regrowth, but part of that loss of root below the surface that still basically becomes food for organisms, but also it sequesters carbon. So you have all that carbon that's in the plant tissue basically being broken down in the soil column, and most of it staying in the soil column. You can actually go to the Chicago Climate Exchange now and buy climate credits for the conversion of landscapes to either prairie or forest, because both native prairie and native forest, because both landscapes have been shown to sequester large amounts of atmospheric carbon. All right, to the guidelines. The first guideline is directed for the mound, but anywhere around the mound, we would certainly recommend having at least 6 inches of topsoil. Again, you're going to need soil structure, you're going to need the right pH, you need to be able to create an environment where plants can thrive, so you need at least 6 inches of topsoil. Do not till on top of the mound. When you're building, of course, please, this is the typical soil erosion sedimentation control recommendation for all sites that are at some time or other have been swiped bare. Of course, you want to establish ground cover as soon as possible. When working in these systems, if these are live systems with wastewater running through them, please take the proper precautions. For instance, wearing gloves. As far as on top of the mound, again, we would recommend non-water loving, or I guess another way to say it is probably shallow-rooted plants, plants that either don't need a lot of water or don't grow very deep roots. No trees or shrubs, please, on the mound. And again, as Dan showed and as we had recommended, offset those trees so that you're at least as far back as the crown of the tree at full growth. Avoid irrigation and fertilization on the mound. Shouldn't need it particularly. I mean, you might need a little bit in the beginning if you're growing fescues, but over time you shouldn't have to do that. Stay off the mounds, please. Do not drive trucks or mowers or what have you on the mound. As Dan talked about, what's going to end up happening is you're going to compact that soil. The more you go over it, the more you drive over it, the more you even walk over it, the more you're going to compact it, and you could potentially lose both the water storage spaces as well as your infiltration rate and have problems down the line. I wouldn't plant edible plants on the mound, no vegetables, no herbs. We would also recommend inspecting the mound at least annually for animal damage. Control animals at the first sign of tunneling and boring. They can do a lot of damage quickly. There are root barriers that you can find. Basically, they're like geotextile fabric with a, I think it's trifluralin. It's a plant growth inhibitor. And we have used those in situations where you're doing like urban tree plantings. You want to keep the roots from growing outside or underneath infrastructure or through infrastructure, but the materials tend to be expensive. And again, if you think about your design, you plan accordingly. You shouldn't have to use root barriers for an adequate planting plan. So again, to sum up on this, I think we would recommend a fescue mix on the top of the mound, and then on the sides, even a little bit on the top. You could mix in low-growing native herbaceous plants, and I'll have a list here in a minute. But some examples include things like violets in the shade, or wild geranium in the shade, or something like a butterfly weed in the sun. The sides and surrounding area can definitely be a mix of native plants and turf. And then as the landscaping and your landscaping plan proceeds away from the mound, you can think about transitioning to shrubs and trees. And again, please, large trees should be offset from the mound at least the radius of the crown. And we mean the crown when the tree is fully grown. So I don't know if I would call this a comprehensive list, but this is definitely a starter for some of these natives. We're talking about things like black-eyed Susan, which is here. Prairie coreopsis, which I don't have a picture of. It has a beautiful yellow blossom. Wild lupine is a tall, upright, pretty purple flower. Here's butterfly weed. As the name implies, it's a great plant for attracting butterflies. Wild geranium here. Prairie smoke, I don't have a picture of here, but it's a beautiful flower. Oxeye daisy, small white flower. Rough blazing star here. Wild bergamot. This is wild bergamot here with a little visitor. And then foxglove beard tongue, another interesting plant. All these are relatively low growing, on the order of 2 feet or 3 feet. We have different blossom times, and represent a subset of the kind of Michigan natives that you could use in and around your mounds. Side oats, grasses and sedges. Side oats grama, little blue stem. Here's a picture of a little blue stem. Prairie dropseed, beautiful grass. This is native, but really can be used like an ornamental in a lot of situations. We've been using it more and more to basically go around certain features that we have because it has such nice ornamental features. June grass, and I want to just move to the next slide here. You see at the bottom a website. That website will take you to SEMCOG, the Southeast Michigan Council of Governments website for low impact development. Low impact development is essentially a technique where you try to act more like stewards and try to replicate more than you do now the kind of hydrologic functioning of a landscape. So you're leaving more trees. You're not clearing and grubbing as much. You're trying to enhance infiltration with infiltration type BMPs. But the reason I bring up the manual is because the stormwater, or the Michigan LID manual available at the SEMCOG website, has as an appendix representative planting lists, and in there, broken up by ecozone, the ecoregion, EPA ecoregion, this is the ecoregion right here. And for most folks on right now, I assume you're in this northern region right here. What the manual will give you, what the planting list will give you, are the native plants for your region. It will tell you how tall they generally grow. It will tell you the color of the flowers, if it flowers. It will tell you if it's shade tolerant. It will tell you if it's salt tolerant. And it will also tell you the kind of hydrologic regime that the plant requires. Is it a dry prairie plant? Can it take a little bit of water? Is it a wetland plant? So while I've given you a couple ideas for plants around mounds, this would be a much more comprehensive listing that anyone could use to start making their planting plan. And that actually is my presentation. Again, the take-home points here. Let us please act as stewards. And the second take-home point is what goes around comes around. Your waste is somebody else's food. So if we think and act and plan wisely, our landscapes can be more ecological, or more soundly ecologically functioning, as well as providing the benefits that we're all looking for. And with that, my contact information, and we've gone quite long, but if there are any questions, I'd be happy to take them.
Okay, Scott, thank you so much. That was a wonderful presentation. I would just like to put in a couple of closing slides here to round out the recorded part of this function, and then I will open it up for questions. Again, thank you to Scott Dierks from JF New and Dan Thorell from Grand Traverse County Health Department. Dan Thorell is also the Secretary of the Board for Wastewater Education. During this year, we're going to be doing a whole series. It says 2010, but it will be 2010 and 11 education courses. And this is just a sample of the things that we're going to be covering online. There'll also be some actual physical meetings at various locations throughout the state. But this will give you an idea of the kind of things that we're going to be looking at this year. The whole theme of this year, again, was Are We There Yet? 21st Century Solutions to Water Sustainability. And the idea that wastewater is not a standalone component, it's part of the water cycle. If we didn't treat and return wastewater to the water cycle, there would be no recharge of water sources, be that groundwater or surface water. That being said, as we pointed out several times throughout this presentation today, maintenance and management are the keys to maintaining water quality. In September 13th and 14th, we're doing part one of a comprehensive on-site system installer training course. This is being taught by Dr. Richard Otis, who, although it says there is President-elect, assumed the role of President of the National On-Site Wastewater Recycling Association just recently. His term will run 2010 through 2012, and Dick Otis is also the technical consultant for wastewater education. And just to remind folks that this will be held at the Benzie-Leelanau Health Department with a video feed up to the Health Department of Northwest Michigan, and that will be held at the Charlevoix office. And this has been approved for 16 continuing septic education credit hours for Michigan. And we just received notice that it's been approved for the same number of hours by the state of Wisconsin. And closing slide here is that so that you can put a face with the voice that you're seeing. There's our contact information. And again, if you would like a written transcript of today's proceeding, just let me know. Be happy to mail one to you or email it preferably. We are a nonprofit organization. We rely on grants and contributions and income that's generated from education activities such as this to be able to do public and provider education. And with that, I am going to close the recording.